Okay, so proof of Cauchy-Schwarz very quickly. Let's do it in the general frame of an inner product, as I've just said that L2 was an inner product. Okay, so let's more precisely take X and some lambda Y. Okay, if I compute the norm of this item, what do I get? Okay, so norm of x plus lambda y is going to be the inner product of x plus lambda y with itself. Well, the norm square, that's going to be the norm square. Okay, so that's norm square of x plus lambda y. Okay, and of course that's greater or equal to 0 because it's just a norm. So let's expand this. You remember how we do that. That's going to be x with x plus we're going to get, well, if I'm going to be to go a bit faster, so that's going to be lambda square y with itself, and you're going to get 2 times lambda x y, okay, because it's symmetric inner product. Right, so and again that's greater than 0. So we get norm of x square plus lambda square norm of y square plus 2 lambdas x y. Okay. Let's divide by norm square of x. Okay, so times 1 over norm square of x. Okay, that whole thing. What do I get? If x is different from 0, of course. If x were equal to 0, well, you don't really have to worry about proving the Cauchy-Schwarz inequality. So if I divide by x squared, I will get 1 here. I will get lambda square times y square divided by x square, and I get 2 lambda divided by x square. So that gives me, let me rewrite this in that order, lambda square y square divided by x square plus 2 lambda xy divided by x square, and I still have this one that comes from the first term. Okay, so what are we going to say? We're going to say that, well, this looks like a polynomial in lambda. That's lambda square plus lambda times something plus a constant. Okay, so I can make the delta. Well, it's what is important is that it's a polynomial in lambda that has a constant sign. Okay, that's always positive. So it's a second order polynomial. It means that it doesn't have any roots. And so the delta, or if I have equal to 0 again, well, let's well, no roots or one double root. So that means delta is smaller or equal to 0. Okay, so let's make the delta of this polynomial. So b squared, that's going to be 4 times x times y squared divided by x, well, to the 4 minus 4 times 1 times lambda square. Sorry, not lambda square, that's our variable, times y to the 4 to the y square, y4. Why would I write 4? Okay, so y square divided by x square. Okay, and that should be smaller or equal to 0. So now let's work on this last expression. Let me divide by 4, multiply by x2. What do I get? We really get that x y square is going to be smaller than y square, and I times times x. Well, I said I multiply by x2, so x2. Okay, in the end, this is what I get. And what is that? That's just the square of the Cauchy-Schwarz inequality. Okay, so if you just take x, y in absolute value, so it's even truer if you don't take the absolute value. Okay, let's keep it. It's going to be smaller than norm of x times norm of y. Okay, we get it's always square norms that it's two norms that we have. Okay, so that was Cauchy-Schwarz inequality, and it's nice if this year you learn this inequality. Okay, let's go back to our LP spaces. What is important is there is no inclusion between those spaces. Okay, so you can take this, for instance, take f of x is equal to 1 over x times 1, 1 plus infinity. Okay, the indicator function. All right, so is that an L1 function? Is this, do we have that the integral of the norm of f is bounded? No, it doesn't belong to L1 because you really know that the integral of 1 over x, whether I consider it close to 0, close to infinity, it's unbounded. All right. Do we have that it belongs to L2? Yes, because you know that if you square this function, so I've put the indicator directly in my bounds. So if I square my function, that's just going to be 1 over x squared. And you know that this is bounded. That's just a typical Riemann integral. Okay, and you remember that indicator times indicator is itself. All right, so that belongs to L2. Does it belong to LP for p greater than 2? Yes, because then you have this one, 1 over x to the p, that is bounded. That's just, again, the Riemann integral. Okay, and does it belong to L infinite? Yes, of course, because its maximum value is going to be reached at x is equal to 1 as it's 1. F in that case is equal to 1, right? Okay, so that was one example. Take another one. F of x is equal to 1 over square root of x times the indicator of 0, 1. Okay, I'm leaving you a few seconds to work these, or a few minutes to work these. You can also try this one, 1 over x power 1 over 4. Okay, again between some interval. Okay, pause the video and try to work, at least for the first one, what are the spaces, the LP spaces it belongs to. Okay, so the first function, of course, is going to be in L1 because the interval between 0 and 1 of 1 over square root of x is bounded. This is also a Riemann integral, but not in L2 nor the next ones. And same thing, well, similar things for the other one. Okay, the x power negative 1 over 4. All right, so let's talk very quickly now about completeness. Okay, so that's a property of some spaces, which means that all convergent sequence have limits inside of the spaces. All converging sequences have limits in that space. Example were more like a counterexample. Q, the set of rational numbers, is not a complete space. Why? Because I can show you some sequences of rational numbers that are going to converge to non-rational numbers. Okay, if you well, maybe you've got a lot of examples coming from the power series. For instance, let me show you this one. Let me define this sequence by 1 plus 1 over 1 factorial plus 1 over 2 factorial plus etc. up to 1 over n factorial. See where I'm going to? Okay, so that's obviously a sequence that belongs to the set of rational numbers because I'm just summing rational numbers. But of course, you all know that when n tends to infinity, that sequence has a limit value, and this value is the Euler number E, which belongs to R and not to Q. Okay, so that space is not complete because we can find some sequences that are converging, but not to a point that belongs to that space. Okay, and so we say that R in that actually is the completion of Q, and that's how we built the or actually the real number as saying, well, the irrational numbers as saying that they are going to be the limits of items in Q. Okay, that's called the Dedekind cut, but anyway, that's not the topic here. All right, so but you see this idea of completeness. Here we're going to have something very nice about that L2 space. L2 is the completion of the set of continuous function of C0 of R. Okay, and more precisely, I can say C0k of R, that sets of continuous function that are non-zero on a compact set, which is just a closed and bounded set. Okay, so again, I'm talking about a lot of new notions that I don't expect you to be able to deal with completely, but I really like you to understand what we're doing here. Okay, so let me give you some example. Right, let me define this function. Well, this sequence of function, it's going to be defined by -1 if x is between -1 and -1 over n. It's going to be defined by +1 if x is between 1 over n and 1, and it's going to be nx if x is in between -1 over n plus 1 over n, and let's say it has 0 otherwise. Okay, so so the support, the compact set where it's going to be non-zero, is going to be between -1 and +1, and that function looks like, sorry, let me use another color, something like this. Okay, something like that. All right. Thing is that it's a nice, well, rather nice, I think, continuous function, except, and it's integrable, and it's which, however, integration you want to make on that, because it's non-zero on the compact set. But if you take the limit as n tends to infinity, it's going to tend to some discontinuous function, which is just -1 on -1, 0. You can exclude it or include it, doesn't matter, and +1 on 0, 1. Okay. Okay, we can even be a bit more precise. It's just something that happens almost everywhere, because actually you can choose what value it takes in 0. It could be 10,000. We don't care. It just happens on a set of known measure. So you can put +1 or -1 or whatever other values. But the idea is that you had a sequence of continuous functions and it didn't converge to a continuous function. So, but it's going to converge to a nice function that is as many times as you want it integrable, and that's what we're going to, well, not prove this, sorry about that, because it would be long, but actually L2 is the completion of C0, okay, in the sense of integrable function, right? And as its norm, so it's a complete set, its norm comes from an inner product, and that's what we are going to call Hilbert space. So if you remember last year, Hilbert space from the mathematician David Hilbert. We talked about pre-Hilbertian spaces, and here comes the Hilbert spaces. Okay, great.